Thank you. Hi there. Well, great to be here. I've actually, when I was invited to come here, I thought, well, a kind of two-day conference in New Zealand. What's the best way of doing that? I think coming for about 2.5 weeks sounds about right. So we've been here 2 weeks, took some vacation, and been all around the South Island and around the North Island and seen all the different bits and pieces. So this has been excellent. Been very happy to be here. So microservices. So if you've been paying any attention at any of the software developer-related conferences the last year, you probably got sick to death of microservices by this point. But what I'm going to try and do is explain why this has come up as an interesting topic. And it really comes down to speeding up development is the thing that we all want to do. And you get there, and I'll show how you get there basically using microservices and Docker and stuff like that, and then a bit about what's next. And then, since that, actually the time when Scott Hanselman saw me was to go to Aarhus when I was still working at Netflix. But I'm going to talk a bit about what am I doing here. I have this very weird job. I work for a venture capital firm as a sort of technology specialist, and obviously I do due diligence on deals. I give advice to portfolio companies. That's pretty obvious. But I also network with interesting people, and that's all of you people. I'm going to be here all day, and I want to get to know anybody that wants to talk to me, and happy to connect on LinkedIn or in person or whatever. I also tinker with technologies a bit. I've written some Go code. I'll talk about that later. I'm on the program committee for a bunch of conferences, and I'll mention one of those later that I'm running. And I do lots of internal presentations at companies and also these talks at conferences. And then I also spend a bunch of time with cloud vendors, which is quite interesting. So why am I here now? Well, this is kind of the cloud adoption curve for enterprises. And you can see they ignore stuff, and then they say no, and then say, I said no, damn it, oh no, oh crap, and then they do it. Well, Netflix was a bit ahead of that. In 2009, we seriously dived into cloud and to try and figure out all of that stuff, and we ended up doing microservices as a side thing. This is my Twitter icon, Cloud Unicorn. But what happened at the beginning of last year, a little over a year ago, was that the enterprises really started diving into cloud very heavily. And I saw an opportunity to leave Netflix, and instead of just explaining what Netflix was doing, to actually engage with a large number of companies and try and help them figure out this stuff. So that was 2014, but the other thing that happened that no one really saw last year was Docker. And it went from being on nobody's roadmap to everybody's roadmap from, if you look at the beginning of last year to the end of last year. It wasn't on anybody's 2014 list of things we were going to do, and it just sort of appeared out of nowhere. It's one of the fastest growing phenomenons in technology. And it's one of those things where people are starting to get sick of it because you hear it everywhere. But I'm going to explain why that's interesting. So 2014 was really the year that enterprises really got into cloud, they got into DevOps, they really started figuring out that they needed to change the way they operated to speed up. Lydia Leon, who's a Gartner analyst, said, this is year on year, there was a huge difference. There was the DevOps Enterprise Summit last October, which was what they basically set up to be, instead of the unicorns coming to talk about how we're all doing cloud and we're all clever, it was the horses. It was all of the big enterprise companies, government departments, banks, defense contractors. They all came out and they said, we're actually doing this too. And this is what it looks like when you have 40,000 developers and you're trying to do DevOps. And this is the reorg chart when you've got 15,000 people working in finance company, and that's what the chart looks like afterwards. Nordstrom was a good example. They went from optimizing from IT cost to optimizing for delivery speed, and that's really the transition that everyone's gone through. And it was one of the best conferences from, what's his name? So I can't read this fine print here. But so it was one of the best conferences I've ever been to. So if you're interested, if you're at one of those big companies saying, well, there's all this DevOps stuff and we're not quite sure how to get there, go find the DevOps Enterprise Summit. There's a whole bunch of videos on YouTube which are amazing. So I'm going to talk a bit about product development processes. And there's an assumption based on that process, which is that every time something goes wrong, you add a process step to prevent it going wrong again. Right? You've seen that? You do a push. Oh, it blew up. OK, let's go check to make sure we didn't do that next time, and we'll have a better outcome next time. But what happens then is you build up these really slow, really complex processes that look like scar tissue. And you can kind of see that. If you look at if you ask somebody, what's your process for release? They say, okay, I can see everything that ever went wrong in the past is somewhere showing up in this process. And then you see it in other areas too. If you look at the HR manual, you can see everything that somebody at your company ever did wrong in the history of your company. There's probably a thing in the HR manual that sort of reflects it. You look at the laws of certain countries, and why are laws of countries different? Well, different things went wrong in each country, and some say, well, there should be a law against that. So you end up with these systems where actually you can't actually keep track of all these laws. There's too many of them, and you can't actually follow all the HR policies. It's too complicated. So Netflix basically has no HR manual at all. It has a phrase, act in Netflix best interest. If you don't have good enough judgment to figure out what that should be at any point in time, we don't really want you working here. And that's their approach to it. And very aggressively got rid of process and basically said it should be obvious what to do, and you should build systems that have people doing the right thing. So you have to basically tear these things down, and what you're trying to do is go really fast. And this is what it looks like if you actually get to this continuous delivery kind of end state. What you're trying to do is observe, orient, decide, and act. And every time you get around this loop, you learn something. You learn something about markets. You learn something about your customers. And if you're trying out different technologies each time around this loop, you're learning something about technologies. And the key thing here is that a lot of companies, big old companies with release cycles that take 6 months or a year, they get around this loop 6 months or a year. That's kind of the waterfall cycle, and you learn something once a year. Whereas if you're doing that once a day or multiple times in a day, you're just learning so much more. So what this really looks like is that the observation part is really about innovation. Can you see what you should be doing? Can you figure out that there's a competitor you want to respond to, customer pain point, something like that? So you measured something about your customers, probably. The next thing you want to do is figure that out. This is really where big data comes in, when you're gathering data on systems and things that you've never looked at before. So the way I think about big data, I want to very quickly answer a question that has never been asked before. That's very different to the business intelligence type of thing, which is like, what was last week's sales? That's a very curated report that you will look at every week. This is a question I've never looked at. I've never asked before. I have to gather data from all these different places, synthesize it, clean up some log files and figure it out. So you're modeling hypotheses this time, right? You're not just saying, I should do this. You've got some ideas. And then the culture, plan a response, just do it, share the plans. So this is you're going to empower the developers to actually own what they're doing in production to go this fast. You can't be bouncing everything off an executive for every small change to the system. And then you use cloud to deploy incremental features behind A/B tests, typically. So you're basically very safely doing lots and lots of fast changes. Then you've got you're measuring customers, and you sort of bounce around this thing. Now, if you get around this loop faster than your competitors, it's very disruptive, because when they start lining up on you, you're off somewhere else. And that's the basis of the OODA loop, is to get around this loop more quickly than your competitors. It's very disorienting. So getting around that's pretty good, but if your organization chart looks like this, then you've got a problem, because to get something done, you've got to work your way across this. And there's lots of meetings, there's lots of tickets to file, and you can't get through this whole thing very quickly. So you end up trying to build teams that cut across all of this, that own everything, that can do everything immediately without having lots of meetings. But that's a little inefficient, because everyone starts re-replicating and building their own tooling. So what you want to do is build instead a platform-based approach, where you've got a platform team that's API-driven. And at this point, the way that you know you've got through this process is that in order to get something deployed, there are no meetings and there are no tickets filed. Then you know you've got there. Everything's self-service, everything is done by the people that want to get it done, and you're owning your own code in production. And this is also a change from having project-based teams to product-based teams. You own a product, you own a feature, you own it for the long term, and you own the iterations of that thing, rather than being the team that's assembled to do this project that runs for 6 months, and then a different team is formed around a different project. So that's also a switch we see from sort of one of the fundamental differences between the way a lot of enterprises are organized versus the way kind of web-scale companies are organized. So what this really comes down to is if you do this right, you end up organizing your company in sort of 90-degree shift. You end up with teams that own bits of the system being the org chart for the system, and everything falls out of that. So if you start off as fairly small, you're basically starting off building a service with a handful of people or building something. You have a bunch of developers, you have a release plan, you run it through QA. And the problem, this works well at small scale. It's the way everyone should really start. It's the fastest way to get going. The problem is when you add more developers to it, you get a bug and it blocks the release. And the bug from one developer blocks the output of all the other developers. And then you get a problem in deployment, and again, it blocks the output. So you end up with, Netflix was in this situation building a monolithic system around about 2008, and with 100 developers, one bug would block 99 developers, and it just got too painful. We had to split this apart. So we went to this immutable microservice deployment model where we have lots of release plans, lots of independent release vehicles, lots of separate services, and they're all happening independently. And then you can start playing around with different technologies as well. But now you've got the different deployment pipelines for all these technologies might be different, so you need a standard way of dealing with that. And what Netflix built was a container-based deployment system using Amazon machine images, because that was kind of what seemed obvious for us. Anything you could jam into an AMI, we could figure out how to get into production. We didn't really care whether it was in C++, Java, Python, whatever. You could do it. Nowadays, Docker's really taken over that role. It's a much more lightweight container. It's more flexible. There's better support for it. And Netflix, in some ways, is starting to migrate to use Docker as well. Now, if you get a bug, you just redeploy that one piece, right? You're done. You didn't have to block everybody else. So this is unblocking larger teams as they scale is really important. The other thing Docker gives us is a standard set of components to build from. So you get this Docker hub, and if you want to run Redis and Nginx or whatever, there's really no reason to go build those machines yourself. You get the standard container, you drop some config files on it, and you're done. And then if you're developing code in Go, you go to the Docker Hub and you get Google's basic image for running Go, which has the latest runtime, the latest operating system. It's a debugged thing. There's thousands of people also using it. And every time there's a bug in it, or whatever, Google revs it. So you just keep pulling the latest standard contain base image, right? So now you don't have to maintain these base images. There's less to go wrong. You're sharing bug fixing and things with a larger team of people. So that just speeds things up. Okay. So that's kind of what it looks like when you get the development side doing. But now the question is, you've got something running in production. You're changing it all the time. You don't actually have time to go and explain to operations guys, hey, I just made this change. Oh, an hour later, oh, I made another change. And there's no one else. You can't communicate with ops fast enough to actually have them support what you're developing. So this is where it comes down to run what you wrote. You are on call for it. So what that looks like is we have a whole bunch of developers. They have a bunch of microservices that they own and that they're owning in production. And if anything goes wrong with one of them, there's some automated monitoring tools that use something like PagerDuty to call that developer. Right, and he gets called directly. Because of the containment of having lots of separate services, it's pretty obvious when one of them hits a maximum CPU or runs out of file descriptors or something, right? It's contained to that one service, and you know who owns pushing that service into production, so you just call that person, right? So it turns out when developers are on call, they get really good at building things that don't break. Right? And that feedback loop is really important. When you put somebody else, oh, it's their problem, they'll get the 3 a.m. call. Well, it turns out they get the 3 a.m. call, and they have no idea what state it's in. They end up calling you anyway. So it's a fantasy that you wouldn't be on call. There is also a site reliability team. but they aren't in charge of fixing things in production. They're in charge of detecting that something's broken and telling whether it's just an internal problem, which means just call, email the developer or call them, or whether it's a customer visible problem, in which case there's an incident life cycle that they manage. And they also manage the availability metrics, where you want to, instead of measuring the percentage of the time that you're up, you want to measure the percentage that your customers are successful. So for Netflix, it's the number of times that somebody clicks on start a movie, whether the movie starts, right? You get to that point. If people can't get to the point or can't actually start movies, that's the thing. So if there's anything blocking anybody from playing movies, that's the availability metrics, the percentage of those against the number we would have expected to see at that point, right? A little bit more sophisticated than just saying we were up 99.9% of the time. Now, the other thing is that if your developer doesn't pick up the call from PagerDuty, their manager is the next one in the call tree, right? And if the manager doesn't pick up the call and get VPs of engineering in the call tree, and this causes people to be pretty good at picking up calls. Again, you build this system. In fact, if you do nothing else to organize your call tree like this, just about everything else will just happen automatically. You'll get nice, reliable stuff running in production. So the problem now is if you start pushing things out and you're building your features, how much stuff should be in a release? So let's just say you've got this monthly release cycle. Every 4 weeks, you're releasing, say, 4 features. And your sort of work in progress is 4, and I'll just sort of baseline how much opportunity for bugs. You've got a certain amount of time in debug, and it takes a certain amount of time to figure out what went wrong. But you've got 4 things in there. When it breaks, which feature broke? It takes a little while to work out which feature broke. And then the QA people always say, we can't quite get this release out every 4 weeks. Can we have more time to test? Has anyone ever asked you that? QA people, we need more time to test this release. So let's do it every 6 weeks, right? So what's going to happen when you do that? Well, your complexity is actually the sort of number of interactions you have. So you can say that the complexity of this release is 16. It's sort of 4 things multiplied by 4 weeks. It's sort of 4 squared. So when you make it 6 weeks, you now have a complexity of 36, which is a bit of a problem because now your probability that you have bugs is 2.25 times higher than the previous release. So even though you've got 50% more time to debug it, there is actually going to be more bugs to debug, and you're going to have more problems. And then QA says, can we extend it to 8 weeks? Because we can't get this thing, and you're on this slippery slope. And I've seen people get to the point where they cannot release anything because they cannot actually get a stable build built. So if you have this problem that you can't get a release out, what should you do? You should actually release twice as often. So if we do that, now we went from 16 complexity to 4, because I only have 2 features in each release, and so 2 weeks worth of work, and there's less and less stuff, and it's easier to figure out which thing broke. So that looks good. But we could just go to 1. Really, what it comes down to is this. If you change 1 thing at a time in production, then you know which thing broke it. It's like absolutely obvious. It's everyone knows that when you want to figure out the impact of change, if you change 1 thing at a time, it's very easy to figure out the impact of change. And this is kind of the end goal. Make it so that you build tooling so that you can deliver 1 thing at a time. And what's happening here is that each time we cut the cost and the size and the risk of change, we can change faster. So now you're kind of releasing 1 feature at a time. Well, that's a problem because tooling involves building this enormous system, and it takes hours, and it takes whatever. But the tooling we have now supports this, and this is why this is becoming possible now. I don't think this was necessarily possible 10, 20 years ago, but with the tooling we have now. Because if you think about using a Docker-based tooling system and say writing something in Go, the build takes a second. Putting in a container takes a second. Maybe running a whole test suite against it takes a few seconds. Deploying it to test or production, everything takes seconds. So now you really can afford to deploy features in seconds. You can just keep deploying features that you can almost deploy 1 line of code at a time into production. And you've got lots and lots of microservices, so you're not redeploying the whole system. You're just redeploying the piece of the system you're playing with. So that's breaking it into small pieces and iterating on those pieces gives you lots of ability to do lots and lots of changes at once. And that's really what it comes down to. So this is kind of a disruptive thing. Once you figure this out, it's a very disruptive advantage for a company to have figured out how to do this continuous delivery with containerized microservices. And this is why the rate of adoption in enterprise of Docker, technologies usually take a year or two to mature and to get into the system. It's taking months instead of years. There are banks running Docker in production now, which is crazy, but it's not even really out of beta properly. So there are people actually pushing really fast. Now, if you're in if this also sounds like I'm an alien from another planet, and some sort of large enterprise companies sort of in that state, you need to get a copy of the Phoenix Project. Have people seen this book? Right? It's a few of you. It's a novel about DevOps and everything going wrong. It's actually a horror story. It opens with a guy driving to work who finds that the VP of Ops and the Director of Ops just got left, and he's the senior guy in Ops. And by the way, Wi-Fi's down. We have a production corrupt payroll run, and the company's about to go out of business if we can't figure out how to get software out. That's the opening, and it gets worse from there. So it really is a horror story. You'll be wincing and going, ooh, I remember that happening to me as you read the book. So it's a good book. It's based on this book, The Goal, from 30 years before, which is about a guy trying to fix a factory so that they don't shut down the factory. This is the same basic idea. It's the best way of getting your sort of management attention to sort of understand the process of the changes. All right, so I've talked about microservices quite a lot, so I'm going to try and define it now. My definition is loosely coupled, meaning every service has to be updated at the same time. You're not loosely coupled, so you want to be able to update things independently. And also this idea of a bounded context, which comes from domain-driven design, and Eric Evans' book on the subject is a good definition, which is about you want to be able to go to this piece of code and say, I know everything I need to know about this code, and I don't need to know about the entire system. So it means bringing on new developers is quick because it's okay, there's these 3 people that are going to call you on this one interface, and you've got like 5 interfaces you're going to call out of. This is your world. You build the bit that goes in the middle, and you need to add this feature or fix this bug, right? That's the bounded context. And because it's a single feature microservice, it just does one thing, it's relatively easy to understand. It's very fast to build. You're much less likely to build bugs into it. You still have to understand how all these microservices fit together, and that's kind of the management architecture layering thing, and a lot of the designing how to get a bounded context is actually what this book is largely about, right? So I'm not going to go through the whole theory of bounded context and domain-driven design, but you're figuring out how to build the right domains, and that's, but you can bring new developers online really quickly. So the kind of things that tend to work against that, I was at the O'Reilly Software Architecture Conference and a few other microservice-based conferences recently, and Sam Newman got on stage and said, I'm just going to get it out of the way. Microservice, Docker, Conway's Law. Okay, now we can move on to the rest of my talk. You'll see lots of people talking about Conway's Law. And this was put up published in 1969, I think. And Conway basically said that the software produced by an organization will end up resembling the communication paths of that organization. So we flip that backwards and say, if we want our software to look a certain way, we'll set up an organization that is structured that way. So you create lots of teams, and you expect those teams to individually build microservices and not to have microservices that span teams, right? And microservices should really be a developer or maybe a handful of developers within one team, and that team then has an API to all the other teams. And that means you can treat something like, say, the Google Maps interface as just another team that doesn't happen to work for you, or any other tool, any other thing that you're consuming via a web service interface is just the same as the guy sitting in the cube next to you. He is just another team with a web service interface. So everything becomes very much like programming on the internet, except you're doing it within your organization as well. So the other problem, and I've seen this as well, is everyone's got lots of microservices, and then once every few months they basically say, okay, let's do alter table on the database and update all our microservices, because they all depend on the schema. And that's a big problem. So you end up splitting your database into lots of different shards and so denormalizing it. And yeah, I know you got taught how to normalize your databases in college, and I'm sorry, but you have to kind of denormalize it now. And deal with the fact that there are lots of databases, and you have to keep them in sync via these messy methods, and sorry. And then there's things like enterprise service buses and protocols where if you've got very inflexible objects, which are very well known across your system, then you can't change everything. You've got to be able to read the next version of an object without breaking, and you've got to be able to read the old version of an object without breaking as well. So you've got to have some version flexibility on things. The other thing that's the trick that we pull here is to have non-destructive production updates. Because if I can throw code into production, which actually is alongside the old code, and most customers are seeing the old code, then I can do that really, at will, right? I'm not breaking anything. So old code remains in service, you deploy a new service group, and then you do traffic routing controls to basically see, these customers that are in this test cell will see the new code, but the old customers don't, so it's very stable for them. And you've got this sort of A/B test, feature flags, version routing, and the first people to see testing. And this is all testing in production, basically, but your QA and your product managers are the first people to see these things in production. You do cohorts of users, and then you figure out looking for a measurable improvement, and if it looks like it works, then you flip everyone over to it. And all of this information I've seen about cohort testing and product ideas and hypothesis is that about 2/3 of all product ideas are either fail to make any difference at all or make it worse. There's only 1/3 of the ideas you have that are actually the good ones. And if you're not doing A/B testing on cohorts correctly with good statistical backing, you actually don't know which third. Right? So your product will meander into becoming worse and worse over time. That's the problem, because 2/3 of your ideas are not good. So very important to just run all these tests. Learning the things that are bad is actually really important because hopefully your competitors will copy the bad ideas. And there's a bunch of people launching streaming services against Netflix, and they're actually copying a bunch of the bad ideas that Netflix knows doesn't work, but we didn't tell them any of those things. So it's kind of a little minefield around the moat. So let's talk about, I've got time here. All right. Speeding up developments. When you deploy something in the data center, it lives there for years at the same IP address, so that's kind of normal. But then when we started putting virtualization in cloud, they have instances that live for a few hours. That's actually, or maybe a few weeks. So these IP addresses become much more ephemeral. Then containers, well, it takes seconds to create them. It might make sense to create a test environment and just run it for a minute and then shut it down again. If you can just automatically spray it with lots of REST calls at thousands of requests a second, you can actually test stuff pretty quickly. And then AWS came out with Lambda, which is it's a container that exists for the duration of a single request and then goes away again. You run a node or something in it, or Java command in it, and you send one event to it, it processes it, and it shuts down again. So now you think about, well, they charge by the 100 milliseconds, and you get the first 1 million requests a month for free. The second 1 million costs you 20 cents, so you have to watch out there. But measuring CPU usage once a minute, which is the way we typically monitor machines, makes no sense at all in this environment. And figuring out, what does it even mean to be measuring CPU usage of a Lambda system? So coping with rate of change, if you're trying to build monitoring tools for this new environment, the rate of change is a really key problem that we're trying to figure out. Here's a bunch of books that I think are interesting to go look at. This is some of the inspiration for microservices and cloud and things like that. So domain-driven design and a bunch of the principles of product development. Flow really makes the case for making all of your changes to production or your product ideas as small as possible. If you've built a really, really reliable system, it will start to break in increasingly strange, Byzantine, and unexpected ways, because that's the only type of failure mode left. Drift into Failure is a really good book about that. Don't read this book if you're on a plane or have a loved one in hospital. Most of the things it discusses are people dying because of planes crashing and things like that. But if you're trying to build a really, really reliable service, then these failure modes and the way that they gradually build up and gang up on you in complicated ways, it's really important. So also I was looking at the state of the art in microservice architectures. I did a talk at DockerCon Europe where I went through this in more detail than I will today. But depending on what sort of platform you're trying to build, there are different microservice architectures to go look at. Obviously, Netflix OSS, so I'll talk about that one a bit more because that's where I come from. But also, Twitter have built, if you're in the Scala world, you're probably looking at what Twitter and Gilt have done. They've built and open sourced a whole lot of interesting tools around Scala. The Groupon and Walmart Labs and people like that have been doing a lot of work around Node. And so there's a whole bunch of Node-related microservice things. And if you're playing around with Go, it's worth looking at what Halo have done. Go is very much an emerging area right now. There's a lot of activity there in the microservice architecture. It's not really any kind of finished sort of, this is the standard pattern, but there's a lot of experimentation happening right now. It's moving really fast. So if you're trying to build microservices, you have to worry about all of these things. You need some tooling to get the things built and deployed. You need some way to configure things in production. You've got to have a way that the microservices can discover each other. You've got to find how to route traffic between them. You've got some observability problems, like how do you find out what is the path of requests flowing through the system? Then you've got to figure out what data stores you're going to run under it, what's your orchestration deployment infrastructure, are you on a cloud or in your data center? And then it's usually somewhat language and container specific. So if you're in the JVM world, there's a whole bunch of options you'd have that would be different if you're doing JavaScript or Go, right? So the Netflix sort of collection of things, there's a lot of names that we let our developers name their own open source projects. So there's a random collection of Greek stuff and Norse gods and other random things here. But what we've got is tooling, configuration, discovery, and then routing and observability, all these different pieces. But Netflix has a nice ephemeral data store model. Dynamite is a way to make Memcached and Redis look like a distributed data store. Very powerful tool. Asternax is a Cassandra client library. It's pretty powerful. And then Stash is a data access layer that knows how to talk to both Cassandra and MySQL at the same time. So you can use it for migrations. And then they do their deployment on AWS, or you could do it on Eucalyptus or SoftLayer even. It's been ported a bit. Most of what Netflix has done is based on JVM, so Java, Groovy, Scala, Clojure, and then some Python, and then their front end is now moving to Node.js, so the web front end piece. Okay, lots and lots of components. This is the step-by-step if you actually want to get going. The fastest way of getting in, they built a thing. Just look for 0 to Docker. It's a bunch of Docker containers. In about 30 seconds, you can get the core set of Netflix services running on your laptop. They've got a bunch of downsized containers to just fire it up. They're all in Docker Hub, so it's easy to run. And then you can start figuring out what the hell's going on here. There's a lot of different pieces here. And people say, well, what's the overall architecture diagram for this? Well, I'm afraid that's what the architecture diagram looks like. And that's a problem, and this is one of the things that's been bugging me for a while. So there's a problem here that there are just too many types of services, and the way they're chatting to each other is too complicated. But it's not just the number of machines that's the problem. So if you think about what is your hierarchy for deployment, and anybody in their bedroom with a credit card can do deployments with this kind of hierarchy, right? It's standard cloud stuff. You can deploy in multiple clouds even. But you can deploy in multiple continents. You can deploy, there's multiple regions per continent. There's zones per region. You've got maybe hundreds of different service types per zone. There's lots of versions. There's lots of containers. And, in Netflix's case, there's thousands of instances running. So that sets up a fairly complex hierarchy of things to deal with. And the trouble is that there aren't really any tools that can cope with that. So then we want to look at the flow through these systems. And there's a few tools that can do that. Netflix has shown this tool. They haven't open sourced it yet, I think, which sort of shows the request rate, the requests going from step to step. The top right picture here is an App Dynamics view showing a fairly simple thing. So App Dynamics works at a fairly small scale, but after a while it sort of runs out of the ability to render things. And the bottom right is from a Twitter tool called Zipkin, which is actually emerging to be pretty much the standard for doing this. Zipkin's been ported to other languages. There's a Go version of it and a bunch of other versions of it. But that basically sets up tags for all the requests. So as the request flows through the system, you can actually gather all the data and reconstruct what the flow looks like. So these are the architecture diagrams for a bunch of interesting microservice things. It's not just Netflix that has what I call the Death Star. There's the Halo and Twitter and Group. Yeah, they all look like that. So flow visualization is a big problem. All right, so failures. How do things fail? Well, if you've got an architecture that looks like this is a sort of simplified view of a Netflix architecture broken out. You've got a load balancer, it's talking to an API proxy, there's some business logic layers. Everything, you see these 3 groups there. Each of those is separate availability zones. So the load balancer spreads the traffic across zones, and then you stay within the zone to just chat amongst yourselves. And then you hit a data access layer that goes back to the Cassandra system in the back end, which is where all the data is moved across zones, right? So this is a relatively generic, fairly simple architecture. So what goes wrong with it? Well, that goes wrong with it. It's an availability zone. The point of an availability zone is they might go away. There might be a plane might land on a data center or a power cut or something might go wrong. And this is a failure mode you should be guarding against, and that's why you run in 3 availability zones, because running on 2, everything is still up. This isn't actually an outage. But what should the monitors show? What monitoring tool what's a monitoring tool going to tell you if you just lost a third of your infrastructure? What it should tell you is don't touch anything. You have no redundancy left. Maybe halt your deployments, right? But don't freak out. You're still running. Customers are still OK. And that's why this is a very powerful architecture, this triple redundant architecture that no master slave, everything is based on quorums. But the challenge here is that there aren't really any tools that will recognize this pattern. So I'm trying to sort of help that process a little bit. And then testing. Let's say you're building a monitoring tool for microservices and you want to test it on 5,000 or 10,000 nodes. Well, OK, you can easily stand that up in the cloud. But that gets expensive pretty quickly if you leave it running for any length of time. So that's a bit of a problem. So one of the solutions for this is simulation. And I've actually built a simulator that tries to help this. And it was mostly just I had an idea and started writing code. It's not my job to do this or anything. So I've written this thing called Spigo. It creates microservices. On my laptop here, I can run a 100,000 node simulation quite easily in a few gig of RAM. All the places where you think it would be HTTP traffic, I use Go channels. So this is a big Go program with lots of Go routines, and then I'm actually dynamically hooking everything up with Go channels, which run at a few 100,000 messages a second, so I can efficiently run a simulation of this thing in my laptop where I'm pretending that I've built a much bigger architecture. I have a basic LAMP architecture, just 4 tiers, and I have a Netflix open source one, and I have some ways that you can migrate between them. It's pretty simple code. So this was generated, this diagram was generated using the thing. It's all on GitHub, it's all open source. I'm checking in code all the time. And then it generates output in JSON format, and there's a D3-based JavaScript visualizer that tries to make sense of it and animate these things. This is what the code to create that architecture looks like. I used some of the names that are similar to the Netflix OSS names, although the code isn't the same, obviously. They're sort of topologically equivalent things. So in this case, the first line creates a Cassandra cluster, and every node knows about itself. So the dependency of the cluster is itself. So those machines actually use a name service to all talk to each other. And then there's a MySQL master slave and some mem caches. And then there's a storage access tier that depends on those 3 tiers, which is the purple dots in that diagram. And then there's a bunch of, I think I said there were Node and PHP processes, business logic that depend upon the data access tier. And then there's what's the Zul one? It's a IPI tier and a whole bunch of other things. But basically, if you have an architecture, just 1 line per tier, you can create this. The tooling wrapped around this then knows how to create that. Basically, we'll set it up as 3 zones in a region, but you can tell it to make multi-region versions of this. And the Cassandra stuff works to hook up the multiple regions. So if you go look at there's a bunch of funny-looking diagrams if you look at my GitHub site. So if you're interested in this, I'm just looking for help. I've already had somebody at one conference fix my JavaScript for me because I'm not a JavaScript programmer. I kind of hacked something together that offended somebody enough that they fixed it. And my Go coding is not actually really idiomatically correct Go programming, but so I'm much more happy playing with Go. If you think this is interesting and you want to generate architecture diagrams with it, I'd be very happy to have help. So why did I build this? I'm trying to generate configurations at scale to actually drive monitoring tools to display these interesting things. And the next things I want to implement, auto-scaling, code pushes, chaos monkeys, things like that. And also have the user interface be dynamically connected to the Go code. This is what the structure of one service looks like. Everything is sent in over a listener channel, and then you just see what kind of message it is and process the messages. And you get named by your parents, say this is what your name is, and then here's all the people to talk to, so that your connections to other services are sent in over your message channel. And then you can do gets, and you do a get request, pass it down, get a response, pass it back up. And then when to quit, make the service quit, you send it a goodbye message. And it responds saying, OK, I'm going away now, right? So, and then there's a service registry that it's polling sort of continuously to see if anyone around it. So it is actually using a real service registry to find all of its buddies. So it's not really idiomatically the way most Go programs are written, but it's more like, in fact, I showed this code to somebody that was an Erlang programmer, and they're very offended that I had not written this in Erlang. So apparently this is more Erlang-y. So what's next? Just got a couple more slides. What's going on next? Well, there's a conference that I'm leading in London in September called Go to London. The Go to conferences and QCon conferences have sort of split off, so there's now QCon London and Go to London. And it's the developer conference, and we're worrying about these three things. How to go faster, be more agile, how to be lean, meaning how to be cheaper and have less waste in your development processes. But in addition, this new concern. Developers, when you own your code in production, you own it, right? You're on call. You're on call if you need to push, if it's broken, but you're also on call if it needs more performance. So you're on call for the capacity and the cost of running it. And you're on call for the security of it. So instead of taking a system and have the developers just like throw it over the wall, we'll wrap a firewall around it, and then we'll say, OK, that should be safe, it doesn't really work nowadays. With microservices, you've got very small identifiable units that can each individually be made very secure. So developers need to be responsible for the security of their systems. And it's not, the ideas about what that means are just emerging now. So there's a talk about that later today that I think you should go and see. But this is a conference where we're talking about rugged development, where rugged is maybe the word that we're going to use to talk about this. If you think this is interesting, Lean Enterprise is an excellent book for leading you through all of the sort of DevOps transformations that big companies are going through. And Building Microservices by Sam Newman. Lots and lots of very good detail on how to break up your databases, how to break up your things, how to do that domain-driven design stuff. It's the best book on that. And then finally, at one point I said, it seems like 2/3 of all the new things that I see are written in Go. That was about a year ago. And then I went, it's like 3/4 of all the new things I've written in Go, and I'm now up to about 90%. I think every new thing I see, and I'm in a VC world, so I see all the new things, pretty much everything's written in Go. So there's definitely something happening around the Go ecosystem. And Docker's written in Go, obviously, but there's something happening there. And I think that if you haven't looked at Go yet, you should try and understand why is it becoming sort of viral in the developer community. It's become the fastest way to get things built. And that's an interesting sort of approach as well. All right, so I'm just about out of time, and we are ready for some NodeBots. But I don't know if there's any quick questions. And this is a list of other talks I've done where there are videos. And these slides aren't on SlideShare just yet, but similar ones are. OK, any questions? Or yeah?
You've mentioned about having very small, effectively a product team of one working on a microservice, and yet with the need for that person, that product team of one, to control security, availability, capacity, be on call. What's the human cost of all this? How do you find people with those abilities, and how do you motivate them to be on call throughout their holidays?
Okay, yeah. So the question is around, if you have a product team of one, how do they manage all of those responsibilities, and how do they go on vacation and things like that? Well, it turns out that people that like to go on vacation. So what you tend to find is you automatically, without even asking for it, get pair programming. So there's always two people that know how anything works. And you find your buddy and you code review with them enough that you can actually have them fix your system. So there's always two people that know how anything's working. I mean, you typically do code review. So you tend to find pairs of people or small teams of people buddying up to look after a collection of microservices. And that gives them the ability to be on call for a week, go off for a week. But there's always somebody on call, right? Now, if that engineer leaves, the manager is now the second person in that relationship. And the manager is then very incented to find somebody else to be the on-call person, because otherwise the manager keeps getting woken up. So the manager gets woken up until they hire a replacement or assign somebody to do it. The other part of your question was about, this is a lot of stuff to worry about. Yes, well, I think that making it the bounded context smaller, so the service only does one thing, makes it easy to reason about. And then there are platforms that understand how to deploy things and do security around things. And so if you're working in a platform that's inherently secure, like the pattern Netflix uses is on AWS. So every service type has a security group with the same name. And in order to call that service, you have to be a member of that security group. So you look at the security group and say, there are only 4 people that could call me. And then I look at what security groups my service is a member of, and I can see these are my outputs. These are my dependencies. So you've now got a very locked down system using effectively firewall rules that are programmed into the way you set up your system. That's just kind of the default way of rolling these things out. You need to understand a bit about penetration testing. You've got to understand identity access management. You've got to understand key management, attack surfaces, things like that. But these concepts are, you're going to have to figure these out, right? This is the way we're going to build robust software, rugged software effectively in the future. I think I need to let NodeBots take over the stage. But thanks, everybody, and I'll be around the rest of the day.